Hello and welcome to this Xilinx Quick Take video, which will briefly introduce you to basic clocking constraints and recommendations with Vivado. Our agenda is simple: a quick overview of clocking constraints, a short demo, and then some links pointing you to where to go for more information. This is a diagram of a basic path from a flip-flop to another flip-flop. A clock net exists, the blue line in the schematic, that is part of the clock distribution network, commonly referred to as a clock tree because it has a starting point or root, and the clock signals branch out to many sequential elements: flip-flops, RAM, DSPs, etc. A clock domain is a constraint that defines critical properties for these synchronous elements, including the period or frequency, the waveform for rise time, fall time, phase, and duty cycle. These properties are used to perform static timing analysis checks for setup and hold in your design. These checks ensure that there is sufficient margin after placement and routing, such that the data arrives and is valid before the clock transitions to capture it, and is held valid for a period of time after the transition. Data is launched from a start point and is captured at the end point, which is where the timing checks occur. Slack is the difference in the data arrival and the required time. If you have positive slack, it ensures correct circuit behavior, avoiding capturing incorrect data and other bad phenomena such as metastability. This particular diagram is simple, but the concepts are the same for more complex circuit topologies, including clock-modifying blocks such as MMCMs and PLLs. There are some important things to keep in mind with clock constraints. They are the most basic of inputs to the tool, and timing analysis cannot occur unless these constraints are provided. In XDC, the primary constraint is the create clock command. Vivado automatically creates any derived clocks that are generated from clock-modifying blocks such as the MMCM and PLL. IP clocks are supplied with core-level XDC files and do not normally have to be created by the user. Our recommendation is to create all your primary clocks, then run some reports to verify that you are not missing any. The timing report summary has a section that reports clock pins that do not have a clock constraint propagating to it. There are some other useful reporting commands to help you discover and analyze clocks: report clocks, report clock interaction, and report clock networks. These are available in the IDE as well as in tickle command form. Obviously, there are some more advanced topics that you might be interested in, such as generated clocks and DDR memory interface constraints. These will be covered in more detailed videos and documentation. In most designs, there are many clocks. A critical difference in Vivado is that all clocks are assumed to be related, meaning if there are paths in the design where data can be captured in a domain that was generated in another, it is reported by default. This was not the case in UCF with ISE. All clock periods are expanded, meaning the waveform is repeated out many cycles, and the tool looks for a common alignment point. If it cannot find one, it uses the smallest window and performs analysis based on that. ISE would not attempt to calculate the timing on these paths unless the user expressly related the clocks. This is a convention adopted by all SDC-based timing tools. You can see that it is critical to carefully analyze paths between clock domains, and Vivado provides reports for this. There are tables of paths in the timing report summary that report the worst paths, if any, found between clock domains, and there is a graphical clock interaction report to help you visualize these paths as well. Designers need to provide input to the tool if these clocks are supposed to be asynchronous, which means they have no known phase relationship, and edges can truly come at any time. The command to do this is the set clock group command, and details of how to use it will be covered elsewhere. The important thing to note is that you're disabling the analysis of paths that really exist in hardware, so you need to be careful and ensure that proper design methodology for clock domain synchronization is followed. Either insert a chain of flops to synchronize, or use a FIFO circuit designed for this purpose. Now we're going to see a quick demo of a basic design with only 3 flip-flops. We recommend you start out with no constraints at all. Analyze the design connectivity, at a minimum at the synthesized design state, and then create constraints as you go, and validate them with reports. Always validate constraints before you launch through the implementation flows so that you do not waste valuable time giving the tools invalid inputs. First, we open the synthesized design, which loads the post-synthesis netlist. We'll open up the schematic view quickly to have a look at the design. We see it has 3 flip-flops and 2 top-level clocks. One comes in directly to a buff G, and another comes into an MMCM and then gets distributed. We'll run a clock networks report. This should give us a good idea of the roots of unconstrained clocks. If we look at our XDC constraint file in the sources view, we see that we have an empty constraint file. This is confirmed by the clock networks report, which has an unconstrained folder, and below that is 2 clock roots which need constraints, clock and clock 2. If we expand clock, we see the distribution of the clock tree all the way through the MMCM. If we expand clock 2, we see its distribution as well. Now we can use the timing constraint editor to create clocks for our top-level primary ports. I double-click on the Create Clock constraint, and it brings up a dialog to specify options. I can enter a reference name and the 2 minimum specifications for all clocks, the period and the root or source, which should be the farthest upstream pin or port on the clock tree. This matches the root of the unconstrained clock tree from our clock networks report view. I can do the same thing for the other clock and specify a slightly different clock period. Remember that all clocks are assumed to be related by default unless constrained otherwise, so you need to analyze the paths between these domains, make sure they are properly synchronized if they're not truly related, then add in the appropriate constraints to mark them asynchronous. Otherwise, any paths found will be valid and will affect the placer, the router, and logic optimization results significantly. We just saw a very brief demo of basic clocking constraints with Vivado and XDC. Please consult the Vivado landing page on Xilinx.com for links to documentation and tutorials to help you get more familiar with Vivado. In addition, there will be more quick take videos available on specific topics to help you learn more. Thank you for watching.